Hi, let's build an image classifier using PyTorch. The key steps are: first, we get the data, then we build the model, then we train the model, and then we test using the model. The last step is also known as doing inference using the model. Let's first import all the required modules into this notebook. Then let's get the training data. To do this, in this example, we're using the fashion MNIST dataset from the PyTorch datasets module. This command downloads the fashion MNIST data into a data folder, and it's only getting the train subset of that dataset. If we look at what the training data object contains, it tells us it's of type dataset and it contains 60,000 samples. It is stored in the data folder locally because that's where we asked it to download, and currently it contains the train subset of that dataset. If you look at the first sample from this dataset, it tells us it's a tuple. That's because we need not only the image, but it also need the corresponding label of that image to train the classifier. So the length of the trained data sample 0 is 2. If we look at the first sample's label, we see that the label is of type integer and the value is 9. This specific fashion MNIST dataset contains 10 object classes, so the values can range between 0 through 9 for labels. If we look at the image itself, it tells us it's of type PIL image, and if we see the image size, it's 28 by 28 pixels. If we actually get the image data pixels and look at the 100 pixel value, it tells us that it's of value 73. We can get the minimum and maximum values of the pixels by calling the getExtremer function on this PIL image, and it tells us the values range between 0 and 255. But whenever we train neural network models, we do not use the raw pixel values as is, but we actually convert them or normalize them in the 0 to 1 range. And also, in case of PyTorch, we want to convert them into tensors so that we can feed the data as tensors into the model. So to do this, we call the datasets.fashion MNIST call again, but this time we say we want to call the transforms.toTensor call, and what that does is it downloads the data but then converts the object into tensors and normalizes them in the 0 to 1 range. If we now look at the type of the training data, it's a torch tensor whose minimum value is 0. The maximum value is 1 because the image has been normalized in the range 0 to 1. Its data type is a float 32, and its shape is 1 by 28 by 28 because it's a 28 by 28 pixel image. And if you look at the first image, the 20th row, we get these 28 values. Let's do the same thing for the test data and download the test data by setting train equals to false and transform equal to transforms.toTensor. Again, what we get is a tensor object whose shape is 1 by 28 by 28 for the first sample, and for the 20th row, these are the 28 pixel values normalized in 0 to 1 range. Since this fashion MNIST dataset consists of 10 types of labels, these are the label names associated with the indices 0 through 9. We can then show some examples from this dataset and view them in a figure. This cell plots 9 images in a 3 by 3 grid, and we can see 9 sample images and the corresponding label in their title. After getting the data, we want to create data loaders. That's because a dataset object gets samples one at a time, but data loaders allows us to wrap a iterable around the dataset and get data in batches. In this case, we are saying we want a batch size of 64, and we wrap a data loader around our trained data dataset and a test data dataset to create 2 separate loaders, trained data loader and a test data loader. Here we see that in the test data loader, we print the shape of the data and the image from the first sample, and it tells us that it has 64 samples because we set the batch size to 64, and each sample has 1 channel, 28 rows and 28 columns. The label itself, Y, is of data type int64, and it has 64 such values because the batch size again is 64. When we train data, we have a choice of running the model on a CPU or a GPU. Preferably, you should have a GPU to train models. This specific command checks if you have CUDA available, and if it is available, the script will try to use the CUDA when it's trying to do training. In my case, I do not have a GPU on this laptop, so I'm using CPU as a device. So obviously the training will be very slow, and as I said, it is recommended to have a GPU device when you want to do training. Before building the model, let's look at all the layers that we need to build the model. If we take a random example X, which is a 1 by 3 by 2 tensor, and we print it out, it shows us these random values, these 6 random values. The 1 here is the number of channels, 3 is the number of rows, and 2 is the number of columns. We can flatten this 3 by 2 tensor into a single vector, and that's done by calling the flatten layer. And what it does is it arranges these values in a sequential order in a vector format. So we get 0.8372, 0.0368, 0.1133, and so on. Next, if we pass in this flattened vector through a linear layer, also known as a fully connected layer, we can first create the layer which is expecting 3 by 2, that is 6 values coming from the flattened layer, and what we want as an output are 4 values. So when we run our vector X, which has already been flattened through this linear layer, we get these 4 output values. Now keep in mind, this linear layer, when we create this linear layer L here, it has been initialized with random weights. So what we see here is a random output using those weights when applied to this specific set of random input. The ReLU layer is a nonlinear activation which is applied typically after a linear layer. In this case, the ReLU layer keeps the positive values as is, so 0.3891 stays as is, but all the negative values are set to 0. So you see the last 2 values have been set to 0. We can then create a sequential set of modules by using the nn.sequential call and list the required layers that we want to use. In this case, we want to first do the flatten, then call the linear layer, which takes in the 6 pixel values and gives us 4 output values, call the nonlinear activation ReLU, and finally again, let's say we want to generate 2 final outputs, then we can take these 4 outputs from this previous layer and generate 2 final outputs. If we now create a random input image consisting of 1 channel, 3 rows, and 2 columns, and pass it through the sequential modules, we can get the output, which we call logits here, and the logits obviously is of size 2 because the final linear layer output has 2 values. We can then pass these logit values through what is called softmax to generate a probability vector. We need this because the values that we get out of the final linear layer do not necessarily sum to 1. To make them as a probability, we want the values to remain between 0 and 1, and their total has to sum to 1. So by passing this through a softmax layer, we can convert these logit values into probability values. The reason we need to give dim equals to 1 is because this is of size 1 by 2 logits, and we want to compute our softmax maximization along dimension 1, that is across the columns. Now that we have seen all the layers and we have got the data and the data loaders, we can actually build the model. To do this, the key steps involved are the following. We have to create a class which inherits from the nn.module, and then we build all the layers of the network in the init function. So as we saw previously, we saw how these layers work. We've seen the flattened layer, we've seen the linear and the ReLU layer, and we have also seen how we can list all of these layers in a stack using the sequential call. The setting up of the model is done in the init function, and the actual data that's processed through the model will be done when we call the forward function. So what we see here is whenever we call this network or this model after it has been built, it will call the forward function, passing in the input into this x variable, which is this. The x variable is first flattened by calling the self.flattened, which was built using the self.flatten in the init function. And then we call the linear relu stack, which was the nn.sequential, and it passes the x vector, which has been flattened here, through the stack and gives an output of size 10. Let's look at some of these numbers. Remember, the fashion MNIST dataset is an image consisting of one channel and 28 by 28 pixels, 28 rows and 28 columns. So what we expect is, after flattening an input image, instead of 28 rows by 28 columns, it will be a 28 by 28, that's 784 length vector. So when we pass that flattened vector into the linear layer, the input of that linear layer is expecting 28 by 28, which is a 784 length vector, and we want 512 as the output number of values from that linear layer. That goes through the nonlinear activation, which is done through the ReLU layer. Then again goes through another linear layer, which takes in the 512 values and generates another 512 values. We again pass it through a nonlinear linearity through the ReLU layer and do the final linear layer conversion by taking in the 512 values and outputting 10 output values. The reason we need 10 output values here is because the fashion MNIST consists of 10 output classes. So what we want are 10 values that the model thinks in terms of the probability of this single input vector x. What is the likelihood of this input vector x belonging to the 10 output classes? So once we have created this class, we can instantiate our model by calling this class function, and we map it to the device, which in this case is a CPU. If we see what the model looks like, we can see that it consists of a flattened layer and a stack of linear ReLU, and linear layers. The input number of features, 28 by 28, is 784 in the first layer, and output features is 512, which again goes into 512, comes out as 512. And finally, in the last linear layer, it takes in the 512 values and gives out 10 values, which are the logits for the class probability for the 10 different classes. So let's pass a random input through this model and see how does it look like. So if we pass in a random vector of size 1 by 28 by 28, we see that x is a torch tensor, a random tensor of size 1 by 28 by 28 containing float 32 values. If we pass this through a model, what we get out is the logits, and the logits obviously has shape 1 by 10 because the final linear layer has output dimension of 10. We can then convert these logits to probabilities by calling the softmax call and doing the softmax along dimension 1. So instead of getting 10 values which are not necessarily summing to 1, after calling the softmax, we'll get values which will sum to 1. So these are the 10 probability values associated with the 10 classes for that single example x that we passed in here, which in this case was a random 28 by 28 image. Since we have these 10 probability values, we can compute the predicted class for this specific random image by doing a argmax along the first dimension. In this case, it says the predicted class is 7. That's because the 0, 1, 2, 3, 4, 5, 6, 7, which is this 0.1070 value, is the highest probability among this 10 values. Just to give a little more information or insight into the model, we can print the name and parameter for each of the named parameters in the model. And here we can see for each layer what are the sizes of their weights and what are their initial random values. So we can see all the layers that are available in the model. Finally, before training the model, we need to set up two key things. One, we need to set up our loss function. In this case, we are using the cross entropy loss, which measures the cross entropy between the predicted probability of a sample and the true output class of a sample. To do the learning, we use the stochastic gradient descent optimizer that will be used with a learning rate of 1e minus 3 to do the learning in this model. Finally, we can start training our model. Here we show the training function call, which is called in a single training loop. The inputs for this training function call are the data loader, the model, the loss function, and the optimizer. We had used the cross entropy loss for the loss function, and we used the stochastic gradient descent for our optimizer. For our data loader, it could either be the test or the trained data loader, and our model is the one that we just created above. In these steps, it goes through the data loader one batch at a time. Remember, we set the batch size as 64. So it goes through the 60,000 samples that are in this whole data set, 64 samples at a time. It sends those X and Y, the image and the label, to the device, which in this case is CPU, but ideally it should be a GPU. We compute the prediction of the model on this sample batch X to get the prediction spread. We compute the loss using the cross entropy loss function call by comparing the predicted values with the actual values of the labels. And then we call backpropagation by calling the loss.backward. And once we have computed the backward losses, we call the optimizer to do its gradient descent by doing optimizer.step. We need to do optimizer.zeroGrad because whenever we compute gradients in this step, we don't want to use the same gradients in the next iteration or the next batch, and therefore we have to always do zero grad every time in this batch call. So we also need a test step because once we have trained the model, we want to test how well does it do. So again, we need to pass in the data loader, the model, and the loss function. Inside the test step, inside the test function, we call model.eval because we don't want to compute gradients anymore. And then for each X and Y, the data and the label in the data loader, which in this case would be the test data loader, we again call model on X to calculate the predictions, and then use the loss function, again the cross entropy loss function, to compute the loss between the predicted and the actual values. We then sum over the test losses and also compute the number of correct predictions by matching the predicted argmax with the actual Y label of the test sample. We then compute the average of the losses over the batches and give the final test loss and the number of correct predictions in terms of accuracy. Here we finally start our training loop. In this case, I'm running the training just for 2 epochs, and for each epoch, which is a set of 60,000 samples, we call the train function, passing in the train data loader, the model, the cross entropy loss function, and the optimizer. And within that epoch, we also call the test function to figure out how the model performs after each epoch. Let's come back when this completes. Okay, the training is completed. We did this just for 2 epochs. We see that the loss started off with a value of 2.301, and as the training proceeds, the loss keeps decreasing, and this is the training loss, and it goes down to 2.18 after the first epoch. In the second epoch, it starts from around 2.17, and finally, after the second epoch completes, the training loss ends at around 1.94. The accuracy of the model right after the first epoch is around 40%, and after second epoch it is around 57%. We can then save this model to our disk by calling torch.save model state dictionary. The state dictionary captures all the relevant parameters that the model needs to know, and therefore those are the values that we store into model.pgh. We can then load this model file by first calling the constructor of our network, net, moving it to the device, and then loading the weights into the model by calling load state dictionary. What this does, it loads all the required weights from the model.pth file by saying weights only equals to true, and then loads those values into the model that was just constructed using this call. Using this trained model, we can then make predictions on a single test sample. So in this case, we see that just after training for two epochs, we grab the first test sample we don't need to compute the gradient on this sample because we are not doing training, which is why we do with torch.nograd. We move the test sample, the first test sample, to device. We call the prediction using the model on this test sample X, and we calculate the predicted and actual values and print out what those labels look like. In this case, the predicted value is ankle boot, the label name, and the actual label is also ankle boot. So in this case, it so happens that the first test sample got predicted correctly just after 2 iterations of model training. Ideally, we want the model accuracy to be high and not 57%, so we can run this for a much longer time, more number of epochs, and then get higher accuracy. So for example, if we continue to train this model for 20 epochs, then at the end, after 20 epochs, the loss decreases to 0.62 and the accuracy jumps to around 78%. And even with this new model, if we try to predict the first test sample, we get the correct label that's being predicted, ankle boot, which matches the actual label, ankle boot. One thing you might have noticed is that in the model, when we created the model, we had the last layer as a linear layer, which outputs 10 values, and these are the 10 logits. We did not add an explicit softmax layer after this linear layer, and that's because the cross entropy loss function that we have included here as our loss function takes in logits as the first argument, and internally it computes the probabilities out of those logits, and so we don't have to explicitly do a softmax to compute the probabilities. One other side note, since the input data here are images, instead of using linear layers, we could also use convolution layers. They make use of local correlations of the data to capture features. So to do that, we can briefly look at how a convolution layer looks like. If I have input data of type 64, 1, 28, 28, that is, we have 64 samples in the batch, one channel, 28 rows and 28 columns. Then if we convolve that with a 3x3 kernel, we get an output of size 64, 32, 26, 26. That's because we are saying the input dimension is of one channel. We want 32 output channels. We want to convolve with a 3x3 kernel and stride of 1. So if you're convolving with a 3x3 kernel, then we obviously lose one on the left and one on the right edge of each row and column when we place the kernel on the image, and that's why the output shrinks by 2 pixels. So instead of 28, we go down to 26. If we take this output and convolve it one more time with another convolution filter, which takes in those 32 channels and outputs 64 channels, again using a 3x3 kernel, our dimension is now 64, 64, 24, 24, again because we have 64 as the batch size, 64 as the output channels, and 24 by 24 as the height and width. We can also use something called a max pool 2D layer. What that does is computes a maximum value from each 2x2 window. So now if we run the previous input through the max pool 2D layer, we'll get a 64, 64, 12 by 12 because the batch and channel dimensions remain the same, but the height and width have shrunk by 2 because we are taking a max in a 2x2 window and sliding the over by 2 pixels. Finally, we could flatten all this input by passing through a flatten layer, and we'll get a 64 by 9216. That's because 64 is the batch dimension and 9216 is the flattening of these remaining dimensions. We can then pass in this 9216 size input through a linear layer and get 128 outputs, and again we can pass it through another linear layer to get 10 outputs because we have 10 output classes. So we can put all of this in a model by creating a new class netconf, which has a sequential of convolution, relu, max pool 2D, flatten, linear, relu, and linear. And in the forward function, we pass in the data through the sequential block and get the logits. So this is another alternative to the linear model approach that we took previously. You can try training using this model and see what results you get. That's all for this video. I'll leave a description to the AI learning via appropriation in the description below. See you in the next one.